every generation believes it has finally begun to understand the universe. For a time, every new discovery seems to complete the puzzle. The laws appear consistent, the equations fit the observations, and reality feels just a little more predictable. Then something unexpected appears. A new telescope peers farther into space. A more precise instrument measures the cosmos with greater accuracy. A tiny inconsistency emerges where perfect agreement was expected. And suddenly, the picture changes again. Science rarely advances through certainty alone. Its greatest breakthroughs often begin when reality refuses to behave exactly as our theories predict. For thousands of years, humanity viewed the universe as something simple and permanent. The stars seemed fixed in place. Earth appeared to stand at the center of creation. The heavens looked eternal, unchanging, and complete. That comforting vision slowly disappeared as astronomy improved. The invention of powerful telescopes revealed that the night sky was far larger than anyone had imagined. The faint patches once thought to be clouds turned out to be entire galaxies, each containing hundreds of billions of stars. Our own Milky Way was no longer the entire universe. It became one galaxy among countless others. Then came one of the greatest discoveries in scientific history. Astronomers noticed that nearly every distant galaxy was moving away from us. More importantly, the farther away a galaxy appeared, the faster it seemed to recede. The conclusion was astonishing. The galaxies were not flying through empty space. Space itself was expanding. This realization completely transformed modern cosmology. If the universe is expanding today, then billions of years ago everything must have been much closer together. That idea eventually led to the modern Big Bang model, not an explosion into empty space, but the rapid expansion of space itself from an extremely hot, dense beginning. Soon afterward, another remarkable piece of evidence emerged. Scientists discovered a faint glow filling the entire sky. Known as the cosmic microwave background, this ancient radiation is the oldest light humanity can observe. It is the afterglow of the young universe, released nearly 380,000 years after the Big Bang. For the first time, astronomers could study the universe not only as it exists today, but as it existed almost at the beginning of time. It was an extraordinary achievement. The universe now had a measurable history. Its age could be estimated. Its evolution could be reconstructed. Its future could even be predicted. Yet every answer uncovered another mystery. When astronomers measured how galaxies rotate, they found something impossible. The visible stars simply were not massive enough to produce the observed motion. According to gravity, many galaxies should have torn themselves apart long ago. Instead, they remained stable. The simplest explanation was that an invisible form of matter surrounded every galaxy. Scientists named it dark matter. To this day, no one has directly observed it. Yet its gravitational influence appears throughout the cosmos. Then an even greater surprise arrived. Researchers expected gravity to slow the expansion of the universe over time. Instead, observations revealed the exact opposite. Expansion is accelerating. Something is pushing galaxies apart faster and faster as the universe grows older. That unknown influence became known as dark energy. Together, dark matter and dark energy now appear to make up almost 95% of the universe. Everything we can see, stars, planets, gas, dust, and even ourselves, represents only a small fraction of cosmic reality. It is a humbling realization. Humanity has mapped countless galaxies while still knowing remarkably little about most of the universe itself. For many years, this model explained observations with impressive accuracy. Computer simulations recreated the large-scale structure of the cosmos. Measurements matched theoretical predictions. Modern cosmology entered an era of extraordinary precision. But increasing precision has an unexpected consequence. The more accurately scientists measure reality, the easier it becomes to notice the smallest disagreements. Those tiny disagreements may become the next great discoveries. Today, the newest observatories are looking farther into space than ever before. Because light requires time to travel, looking farther also means looking deeper into the past. Some of the earliest galaxies appear surprisingly large, surprisingly bright, and surprisingly mature for such an early stage of cosmic history. They do not necessarily contradict the Big Bang. But they suggest that galaxy formation may have progressed faster than many earlier models predicted. At the same time, another puzzle has captured the attention of cosmologists around the world. Different methods of measuring the expansion of the universe produce different answers. Observations of the early universe suggest one expansion rate. Measurements of nearby galaxies suggest another. If the Hubble tension has taught scientists anything, it is that the universe may still be hiding important pieces of its story. For decades, cosmologists have treated dark energy as a constant property of space, an invisible force causing the expansion of the universe to accelerate. This assumption has allowed researchers to explain countless observations with remarkable success. But what if dark energy is not constant at all? Some scientists are investigating models in which its strength changes over billions of years. Even a small variation could alter how galaxies formed, how quickly cosmic structures evolved, and even how old the universe appears when measured using different techniques. At the moment, no evidence has settled the question. But the possibility is important because it reminds us that every scientific model is only as strong as the observations supporting it. Gravity presents another fascinating mystery. It is the weakest of nature's fundamental forces, yet it shapes the largest structures in existence. From planets orbiting stars to galaxies gathering into enormous clusters, gravity quietly governs the architecture of the cosmos. Yet researchers still cannot fully explain how gravity fits together with quantum mechanics. General relativity describes the universe on enormous scales with extraordinary precision. Quantum physics explains the microscopic world with equal success. But combining both theories into a single mathematical framework remains one of the greatest unsolved challenges in science. Some physicists believe that solving this puzzle could transform our understanding of space and time themselves. Meanwhile, the universe continues revealing astonishing patterns. Galaxies are not scattered randomly across space. Instead, they form an immense network known as the cosmic web. Enormous filaments of matter stretch across hundreds of millions of light-years, connecting vast clusters of galaxies like threads in a gigantic three-dimensional network. Between those filaments lie enormous cosmic voids, regions containing remarkably little visible matter. This structure developed over billions of years as gravity slowly amplified tiny differences left behind after the Big Bang. Yet researchers continue studying how these enormous patterns formed so efficiently during the universe's early history. Some models explore the possible influence of exotic particles. Others investigate whether unseen forms of matter behaved differently shortly after the universe was born. Still others examine whether gravity itself may act differently across the largest cosmic distances. Each possibility is carefully tested against observation. Most are eventually ruled out. A few survive and inspire entirely new directions of research. Modern astronomy is not searching for dramatic shortcuts. It is refining our understanding one observation at a time. Another powerful tool helping scientists investigate these mysteries is gravitational lensing. According to Einstein's theory of general relativity, Massive objects bend the path of light traveling nearby. Entire galaxies and galaxy clusters can act like enormous natural lenses, magnifying objects hidden far behind them. By studying these distortions, astronomers can map invisible matter that cannot be seen directly. Again and again, the results point toward the same conclusion. There appears to be far more mass in the universe than visible stars and gas can account for. Something unseen continues shaping cosmic evolution. Perhaps the most remarkable realization is not that scientists still have unanswered questions. It is that every generation uncovers entirely new ones. Ideas such as the multiverse, cyclic universes, or the emergence of spacetime from deeper quantum processes often capture public imagination. These concepts remain speculative. They are not accepted descriptions of reality. Instead, they represent attempts to explore possibilities whenever current theories leave important questions unresolved. This willingness to investigate alternatives is one of science's greatest strengths. It allows knowledge to grow without assuming today's explanations are the final ones. History has repeatedly shown that better instruments lead to better questions. Each new telescope reveals structures that previous generations never imagined. Each improved detector uncovers details hidden within familiar observations. Every advance reminds us that certainty is temporary. The universe is not becoming stranger because nature is changing. It is becoming stranger because our ability to observe it keeps improving. Perhaps that is the most inspiring lesson of modern cosmology. We are not standing outside the universe looking in. We are part of the very history we are trying to understand. The atoms that form our bodies were created inside ancient stars. The light entering our telescopes has traveled for billions of years before reaching Earth. Every observation links humanity to a story that began long before our planet existed. And that story is still unfolding. With every new mission, every improved simulation, and every unexpected discovery, another page is added to humanity's understanding of the cosmos. The universe has never promised simple answers. Instead, it offers something even more extraordinary. An endless frontier where every solved mystery reveals another horizon waiting beyond it.